She's always present.
I know. Look, see, I told you, he'd sign every
I have my glasses on.
Wait, you're not supposed to sign all of them, though. There's only specific days.
That's what I thought. And then she said, sign whatever you want to sign.
No, yeah,
So I just kept signing.
No, look at how good I am.
All right, we're starting math.
Highlight.
So this up here is a surface. And the question says at what points are the following functions continuous? So whenever we're thinking about continuity, we're thinking about basically where is it not continuous, and then wherever it's not continuous, we leave those points out, and it's continuous everywhere else. So when we look at that, anyone know what that surface is? Anyone know yet? If I wrote it like that? We squared both sides and did some addition. Does it become obvious what that surface is? It's more than a circle.
Sorry, a sphere.
So, and because this is the positive square root, that's going to be the upper hemisphere of the sphere of radius 2 centered at the origin. Okay, so in terms of the terms of continuity, what would we say in terms of continuity? Where is this function continuous? It's going to be continuous at the set of x, y,
where x squared minus y squared is not equal to 4.
So could it be greater than 4? X squared plus y squared?
No, x squared plus y squared must be less than or equal to 4.
Right. So when we're looking up here, this square root is going to be defined as long as what's in here is going to be greater than or equal to 0. As long as what's inside the square root's non-negative, you're good to go. So this says if we rewrite this in a more readable way, we're talking about all the points within and on the boundary of the disk. That's where this function is defined. So first and foremost, for a function to be continuous at a point, it must be defined there. A function can't be continuous at a point that's not in the domain. So this is the group of points where it's defined, and that will be the same set of points where it's continuous. So the set of x, y such that x squared plus y squared is less than or equal to 4. That's where we will have continuity. And when we talk about continuity at a boundary point, so if we were to draw a picture of this domain, is sort of like that, a disk of radius 2 centered at the origin. When we're investigating continuity in the one variable case, you could talk about left and right continuity. But here, we're imagining our surface is defined on this. And to be continuous at a point here, that means that it must be continuous along all these paths that lead up to that point. So we can't go outside the disk. So when we're analyzing continuity at a boundary point, we're imagining that all the paths that lead to that point have the same thing is going on. It's got to be continuous along all those paths. All right, let's take a look at this one. Let's see. Okay, so we have, let's first talk about, when we talk about continuity, it means that the limit exists, and it means that the value of the function exists, and it means that they're the same. So continuity, limit, and value exist and are equal. Limit of the function, value of the function are equal. So the question here is, the only real point in question is the 0, 0, because this function up here, the denominator is always positive or 0. But the way that we've restricted it here, we're implying that this whole denominator is always positive because we're not including the origin there. So that's always positive. And in the numerator, we have a continuous function, and if we divide by a continuous function, you still have a continuous function everywhere except at the origin. So the question is, with that redefinition of the value of the function at 0, 0, does that make this continuous? So in a one variable case, it's easier to sort of picture what they're talking about. So if you have a situation like this, where you've got a function that's continuous everywhere except for that one point, I'll just call it C for the heck of it, So maybe there's a division that creates a hole. That number is not in the domain. But if you redefine the function to be equal to whatever that value is right there, now it's continuous. So that was a removable discontinuity. In contrast to something like this, where we might have a hole and a gap, then here this function is continuous to the left of C, it's continuous to the right of C, but it's not continuous at C, correct? It's not continuous at C. This is continuous at C if we fill in the hole. But if you fill in the hole here, it's still not going to be continuous at C. Everybody follow that? So the top one's called the removable discontinuity. The bottom one is just a discontinuity. Can't remove it. You can't define the function value at that point to be anything that's going to force those two pieces to have no break. So here the only issue is the origin. So the question is, okay, well, the value of the function is equal to 0 there. Now we have to check the limit of the function. Is the limit of the function also 0? And if it is, then it's continuous. If it's not, then it's not continuous. So we have to take the limit of this. And this is a really good opportunity to, we're going to talk, well, it'll be here in a minute. I'm going to introduce the idea of converting to polar here, because this is a really good example where we can convert to polar and have it work well. So you all know that the polar conversion involves two equations. When we are comparing polar to Cartesian, we are letting x equal r cos theta, y equal r sine theta. And the primary equation that we get from this is that x squared plus y squared is equal to more than 1. More than r. R squared. Yep. So let's think about this for a second. What my claim is going to be this, and then let's explain it in a second. So I claim that we can rewrite this as follows. That's equivalent. That we can take this 2-variable limit and convert it into a 1-variable limit. So the question is, does that make sense? And so if you think about it, and this only works when we're going to the origin. It does not work in general. You can't just convert to polar regardless of where you're taking the limit at. You have to be taking the limit at the origin. The limit at the origin can be converted to this because if you imagine polar coordinates and you imagine the origin, isn't it true that if x and y are an ordered pair in the plane, and if you force r to be going to 0, so if r is going to 0, doesn't that imply automatically that x must be going to 0 and y must be going to 0? If you're forcing a point to get closer and closer to the origin, and that's what r represents, distance from the origin. So if you're forcing your point to get closer and closer and closer to the origin, that means that x and y are getting ridiculously close to the origin also. Correct? So in the one case where the limit is at the origin, we can convert to polar with these equations. And then we can use L'Hopital's rule if we need to. Because L'Hopital's rule only works with 1-variable limits. 1-variable calculus. So right now we have an indeterminate form. 0 on top, 0 on bottom. Limit of an indeterminate form can be evaluated by taking the limit of the quotient of derivatives. And we're taking the derivative with respect to r. So we're going to get a 2r. Up top, derivative of cosine is minus sine. So that's going to be sine of r squared multiplied by r, as r goes to 0. And then the r's, there's an r that cancels. And what is that limit? Everybody agree? Sine of 0 is 0. So we've now created a fraction that is defined at 0. So that means that the limit of this expression here is 0. So now we have that the value of the function is 0. That's the value of the function at the origin. And we also have the limit of the function being 0. So if the value and the limit are the same, that means the function is continuous at the point in question. So therefore, continuous at the origin. Yeah?
So could you, instead of doing 1 minus cosine of r squared, could you replace that with a sine? Like a sine squared?
No,
You couldn't?
because that square is on the r, it's not on the cosine.
Oh, okay.
Do you see it?
Yeah, I see it.
Right, so that is cosine of r squared, not cosine squared of r. If it was cosine squared of r, definitely, we would go sine squared. Yes.
Did you multiply by r because it's r squared? My brain says it should be 2r for the
Yeah,
derivative.
that's kind of why.
Oh, yes, that should be, you're right.
Oh.
Yeah, when we take the derivative of that, it should be 2r, thank you. Oh, yes. Thank you. Yeah, derivative of r squared is 2r. Good observation. Doing your job.
So because it's
You're gonna get a
continuous
good
at that
tip.
point, it must be continuous at all points, yeah?
All points in the domain, yes.
Okay.
And this, is there any restriction on the domain here?
I don't think so.
So you're telling me that I can plug in x equals 2 and y equals 2 and this would be defined? So cosine of 4 exists?
No. Think so.
So it's continuous on its domain.
Okay.
Continuous on its domain. So if the question said, what is the domain here, we'd have to say, oh, okay, well, for cosine to be defined, x squared plus y squared has to be less than or equal to 1. Oh, did I say that? Oh, what the heck am I talking about? Cosine of 4 is defined.
I thought
I'm
so.
wrong. You're right. You're right. There's no
For a
restriction.
second, I was like,
No, you're
is
right.
everything I know a lie?
Yeah. Oh, God. So I was thinking about the inverse stuff. So cosine is defined at any angle, right? The domain for cosine is all real numbers. It doesn't matter what the real number is. You're thinking in terms of radians. And so if x is 2 and y is 2, cosine of 4 just means cosine of 4 radians, totally fine. Yeah, there's no restriction. So this is defined on all of R2. So the domain is all of R2 here. Yeah. Good point.
If we didn't get 0, what would we do? Like,
Then it's not continuous
It's
there.
just not continuous.
So then we're talking about this situation here.
Ah.
Yeah. Or analog to that situation with surfaces. So you can't, yeah. So the analog with the situation with the surface is that there must be, some sort of tear in the surface. It's not just like a bubble with one point taken off, right? It's got some sort of gap that you can't mirror with one point. All right, so some reminders from Calc 1. This is one of the common ones you analyze in Calc 1 where the limit does not exist at the origin. So here, sine of 1 over x, there's no single number that it approaches as you get closer and closer to the origin. So this was just a classic example of a limit that does not exist. And I'm just pointing these out because these are two that come up a lot throughout math. And they're good examples to just sort of keep in mind. So here, sine of 1 over x times x, that multiplication of x is enough, and it drags the y values to the origin. So this is one where the function is not defined at 0, because you have 1 divided by 0, but this function has a limit and is continuous at the origin. If you redefine, if you do what we just did in the last one, if you say this kind of thing, if you piecewise it out and you say, hey, let's let this be x sine 1 over x for x not equal to 0, and you define it to be 0 when x is equal to 0, now you've got a continuous function. So that discontinuity at the origin is removable. Whereas this is not removable because you cannot define the function at 0 in a way to make this continuous. So that one is not a removable discontinuity. You've got it. It's much more complicated. That discontinuity is removable. It's not defined at 0, but if we change the function, we can fill in that hole by putting the value of the function to be 0. So removable discontinuity, not removable. Okay, limits of functions. Here they just want us to explore. It doesn't matter how many variables you have. You do what you always do. You plug in the numbers, and if you get a number, you're done. So if the function is continuous at that ordered triple, then the limit is exactly what you think it would be. So it's going to be 1 plus 1, natural log, e to the 0 times 0. So if we get a number here, then the limit exists. If we get an indeterminate form, then we have to do more.
That's not 0.
Wait.
It's not?
Yeah, it
No.
is. Natural log of 1 is 0. 0
Oh.
times 2 is 0.
Yep, never mind. Never mind.
Did I skip too many steps?
Also,
Oops.
lateral log of
There
e
you
of
go.
n is n. Since n is 0.
Well, yeah, can't you just like cancel the ln and the e? Almost.
Oh, right. This is natural log of e.
That's natural log of 1, right?
Yeah.
Say that again? Can you cancel out the ln and the e right here?
No, I mean like there. Like once you get.
Yes, you can.
And
Well,
then
you
it's
could
just
also
0.
do it right here. If you have natural log of e to the xz, that is x times z. That's kind of what you're
That's
saying?
yeah.
Yeah, and x and z are both 0, so yeah. Definitely. Everyone agree you can do that? Yeah. Yeah, and you can also do it right here. Just make that 0. Yeah, lots of ways. Lots of ways. So that limit does exist. This one, you plug it all in, you are going to get an indeterminate form here. And so if you get an indeterminate form, you need to try to do something so that you can modify the fraction. And the one thing that we've seen tends to work again and again and again is factoring. If we can factor and cancel a common factor. So if we factor out an x from the first two terms, we factor this by grouping, then we are going to see that we will, in fact, be able to reevaluate the limit and hopefully get something. So when we factor by grouping, we end up seeing a common factor of x plus y. And so that our limit is z plus 5, and we're investigating the ordered triple where z is 1. So this would have a limit of 6.
Factoring by grouping.
Factoring by grouping.
Good old days.
Old school.
Yeah.
Back to basics. Back to basics. All right, any questions on that? So of course, if there's a lot of ways that this could be really complicated and almost unmanageable. If you have a function that gives you an indeterminate form and you have 3 variables, it's got to be cooked up pretty nicely to be able to reduce it to something that you can take the limit of. So it's more the concept that they're asking us to look at there. All right, so same idea here. We talked about polar already. We want to convert this to a limit with just one variable. So we're going to convert to polar. We're going to say that x is going to be r cosine theta, y is going to be r sine theta. And so the numerator becomes r cos minus r sine. And the denominator becomes the square root of r squared, which, okay, let's talk about that for a minute. Okay, so we've talked a little bit about this in the past. We know that the square root of x squared is the absolute value of x. So we have to be a little careful. We can't just take the square root of a square and say it's equal to r, because that's only true if r is positive. Right? So we could analyze this with 2 different cases, or you could, and it's not going to matter, you could do this, which a lot of books will do this. This book doesn't tend to do it. But you are able to do this. You can say, let's just consider going to the 0 through positive r's. Right? If you go to the origin through positive values of r, you're just imagining a positive radial distance. Remember in polar you have that whole negative r thing where if r is -2, you go to the quadrant that's opposite it. We don't have to deal with that. You can just say, if you let r go to 0 through positive values, you still are forcing x and y to go to 0. Right? Even if you go to this origin through positive values, you're still going to get that x and y are both going to 0. So it's totally fine to assume that you're going to go just through positive values. If you're going to go just through positive values, then yes, the square root of r, bless you, square root of r squared is r. The r cancels with each of the r's in the numerator, and we get that. Is there an r in that expression? No. So the limit of a constant is the constant. So this is the limit. Is that a number?
Yeah, well, yeah.
No. It's a number for a very specific theta, but it's not a constant. It's a function. So when we say that for a limit to exist, it means you have to be approaching a single number. And we're not approaching a single number because depends on theta. So this will be a DNE for our limit because this does not approach a single number. So the limit part here is r goes to 0. This expression with theta is constant with respect to r, so it jumps to the front. And there is no r in there, so the limit symbol just disappears. If there's no r, you can't plug r equals 0 anywhere in there, so that just vanishes. So we get that. That is not a number. So for a limit to exist, you have to approach a single number. You have to get closer and closer to a single number.
So let's say we got a problem like this on the test, all right?
Mm-hmm.
And instead of putting RO plus coming in from the right side,
Mm-hmm.
we don't do that. Will
Mhm.
we be docked points?
Well, the other possibility is that you could, I'm not going to put something tricky like that on there where that's even going to be an option. But the other option, if you don't take away the plus, you could do it in two cases. You could say, let's assume r is positive, let's assume r is negative, and in both cases you'll get a DNE. So that's another way you could approach it. You could say, first let's assume r is positive, and then let's assume r is negative, and you'll still get the same DNE.
And if you didn't assume both were positive and negative, like you just straight up dropped the plus and just went through it.
Yep. So the square root of r squared if r is negative is going to be minus r. And so then you're going to end up with negative cosine plus sine. But then again, there's no number it's approaching, so you'd still conclude DNE. So you'd have DNE. And you do know from Calc 1 that if you have a one-sided DNE, the limit does not exist.
Right.
You can't come in from the left and have it be DNE and come in from the right and have it be 5. Your conclusion would be the limit is DNE. Right? If you have one side that's coming in DNE, then you're done. So you can think of it that way also, that, oh, we got one DNE, then we're done. One DNE. All right, let's take a look at that. So it looks to me like we're in a similar situation. If we plug in zeros, we're going to end up with 2 divided by 2. Oh, no, this just works out fine, I guess. I don't know why I was second guessing. So inverse tangent. We're going to, actually I can take away the limit symbol. Let's take away the limit symbol. We're just going to plug in the numbers and see if it works. So when we plug in the numbers, we plug in zeros, and it looks like we just end up with 2 over 2. So that's the inverse tangent of 1, which is pi over 4. I was thinking we might have to use polar, but we don't. That's not an indeterminate form. Not an indeterminate form. All right. Doing. All done. All right. Off to 12-4. Da-dun, da-dun, da-dun. There we go.
You show that last one.
Oh, grand.
So you would only use polar if you can't factor?
Right. So polar is best used if you have x squared plus y squared, and you're going to the origin, then go polar. And so when I first looked at this, I was thinking, oh, there's an x squared plus y squared. When we square this out, we'll have an x squared plus y squared. So I was thinking, oh, polar.
No.
But we don't have to go to polar here. So if this was indeterminate, we would go to polar. It's not indeterminate. Not indeterminate. So we won't need polar. All right, partial derivatives. Like we've alluded to, when you're dealing with a surface, there are 360 degrees that you can head. There is a rate of change in each of those directions. And there are two specific directions that we want to analyze. We want to analyze going in the positive x direction and the positive y direction. So here we're going in the positive y direction, and here we're going in the positive x direction. So we want to analyze those two rates of change. Those two are going to have specific names. Those are going to be called the partial derivatives. So when you're standing on a surface, there's 360 degrees you can walk. If you walk in the positive x direction, the slope in that direction is going to be called the partial derivative of f with respect to x. So the partial derivative of f with respect to x, I'll write those words down in a minute. Let's just talk about the concepts for a minute. And if you walk along the surface and you look down and you're going along the positive y-axis, that will be the partial derivative with respect to y. So there's an infinite number of directional derivatives. You can go at 2 degrees, you can go at 40 degrees, you can go at 90 degrees. But if you go in the direction of the positive y-axis or the positive x-axis, those two are called the partial derivatives. The rest are just called directional derivatives. So rates of change in a particular direction. Yeah?
The physics department of Front Range is pulling an elaborate prank on its students because
Shocker.
Calc-based physics 2, which requires only calculus 1, has lots of stuff involving partial derivatives.
Lots of stuff.
Yeah, it's like integral to the way they make you handle uncertainty.
Interesting.
And they do divergence gradient curls.
Yeah.
What?
Does.
They do divergence
Divergence gradient curl.
in
Yeah.
physics 1,
Physics 2, that's what I hear.
Yeah.
in physics 2.
Which
Physics
only has
2.
Calc 1 as a prereq.
Yeah.
Physics 2 only has Calc 1 as a
Yeah,
prereq?
Calc-based physics 2 has Calc 1.
And they're doing divergence? Oh, interesting.
Yeah, so
Because that's what we're doing in here, right? We're going to do divergence here.
That's rough.
Good thing you waited.
I waited.
Interesting. Wow.
As
I mean, hopefully they're doing easy enough partials that it's not too complicated.
I don't really think they put any restrictions on it because you have to use it for your like semester project. So I guess how hard it is depends on how hard of a project you
The
chose.
function you end up working with. Wow, interesting. Well, let's get it going then. So when you look at this picture here, do you think, and we usually think of f sub x as the partial in the x direction and f sub y as the partial in the y direction. So which one of these do you think is positive in that picture? So one of them is positive, one of them is negative.
Which point?
The point right there.
Oh, okay.
So the partial in the y direction is
Negative.
negative and the partial in the x direction is positive. So this is a little different than one variable calc also. In one variable calc you didn't talk about directions. So in one variable calc, if you had this function right here, you are always assuming that the derivative, you are going left to right. You don't pick a point and say, okay, if I come in from the right to this point, the derivative is negative, and if I come in from the left, the derivative is positive, right? You always assume you're reading left to right. So the slope of the tangent right there is positive because that line has a positive slope. So this is a little different. In multivariable calculus, when we look at this point, let's look at this surface right here. So the direction in this direction, the slope in this direction is down. The slope over here is also down. Right? So both of those will have if you go in the north or south direction, you're going to have a negative directional derivative. You're going to be going down. So with this one variable case, you're always looking in this direction. You don't come in this way and say, oh yeah, we're going down. No, it's positive derivative. Always going left to right. All right, so here is a great little picture. In the online book, in the interactive textbook in the website, in my math lab, they have a lot of these things that are interactive. I should have looked. I was looking at them the other day. I should have brought one up, or maybe I can bring one up during the break. But they have a lot of these interactive figures. If you go into the multimedia library and then click on interactive figures, they have a lot of these where you can sort of grab the curve here, the intersecting curve, the trace, and slide it around and just see how it works. So those figures are pretty cool to play with and get a better sense of how it all works.
Many things need a Wolfram Alpha on your computer, right?
You need the CDF player.
That thing's the worst.
The CDF player, you need the worst CDF player available. Yeah, it will tell you, if you just search CDF player, it will come up. But it works pretty well.
I just think that a 2 gigabyte web browser extension is an atrocity. But
Is it 2 gigs?
And I think the program
it's
in
awful.
and
Is
I
that
think
right?
and I think the
Yeah.
standalone program is even large, like 6 gigabytes maybe.
That's why I had to buy a new laptop.
Yeah,
I remember
I have
now.
a suspicion that maybe it can't calculate anything, and it just has like a billion JPEGs of different graphs, and it like picks one depending on what you type in.
Oh, let's hope not. Wow,
Seriously,
2
why can't-
gigabytes for that player? That's crazy.
Why can't they
It's
just
for real,
make
though.
it like a web app? That's what everyone's doing these days.
Okay.
It'd be so much easier on the consumer.
Okay, so let's look at
Written down
this.
script.
So you see that curve there. So that curve is a cross section where we're varying the function in the x direction but not in the y direction. Does everybody see that this is going to be a curve that we're going to be talking about the rate of change in the x direction? Because the y direction there, it's fixed at b. All the y values here are b. Right? The z values are changing. So when you're doing this partial derivative with respect to x, you're measuring how is the function value z changing as x changes. Everybody follow that? So here we've set y to be constant at b. So this curve right here, we're finding f sub x at this curve, at this point right there on the surface, which is also on this curve. Everybody follow that? So that point right there, we're going to talk about f sub x. That's the rate of change in the x direction. So we're imagining this intersecting curve through our surface in the x direction going through the point that we're analyzing. So here we would find the slope of the tangent, and that will be the partial with respect to x, whatever that slope is. Now down here, they've drawn the tangent line. So whatever the slope of that line is, that's going to be f sub x at a comma b. F sub x is the rate of change in the x direction at the point a comma b. A comma b, though, is down in the domain. There's a comma b. So then the rate of change is the slope of that tangent line. So f sub x, rate of change in the x direction, positive x direction. Positive x direction. Here is what the partial derivatives look like mathematically. So let me also say that we use this notation. You will see both these notations. The subscript notation is like the prime notation. We tend to use the prime notation because it's simpler and easier, and most of the time it's just fine, as opposed to the differential notation. So this is differential notation, dy dx. This is prime notation. You can do partial derivatives with differential notation, and then you use a script d. And you'll see that in all the math, the math equation editor things, that you can have that d. So this d implies that the function is a multivariable function. And so that's a partial derivative as opposed to a full derivative. So that's a partial derivative. It's a partial because there's 360 degrees that you can walk in. So you can't just take a derivative because you have 360, there's a whole myriad of places to go, directions to go. All right, so let's analyze and make sure that this limit, you're used to this difference quotient. That's what the definition of the derivative is. It's a limit of a difference quotient. So notice that the x-coordinate is changing, right? X plus h is getting a plus h, not x plus h, a plus h is getting closer to a as h goes to 0. So we have constant, we've set the y-coordinate not to move. So it's just like the picture we just looked at right here. The y-coordinate's not moving if you go in the x direction. So the y-coordinate is fixed. So here we sort of see it fixed at b, and the only coordinate changing is the x-coordinate. So a plus h is approaching a. So it's just like the difference quotient that you use for a regular derivative, except that there's two coordinates. One of them we fix. And similarly, for this one, we're going to let the y-coordinate change, and we're fixing the x-coordinate to be a. So those will be the formal definitions. We'll use these less than you used the formal definition of the derivative in Calc 1, which is good because those are very, very, very hard to use when you're dealing with a multivariable function. We won't even do it once. It's so hard to do. We're going to do it, the easy way, like the power rule way. You first learned that limit of a difference quotient, and then like 5 days later you learned the power rule, and you're like, why did you wait 5 days to tell me the power rule?
Yeah.
Like, what? What? So f sub x, and now of course if you want, this is your preference, if you want to put the independent variables in here, you can. Most of us just write f sub x because it's notationally simpler. Most of us will just write that. Doesn't matter though. It is a function of two variables. So f sub x is still a function of two variables. Here you just are kind of underscoring, hey, just remember we've got two independent variables here. But you don't have to do the of x, y. It's totally up to you. So f sub x, that's the rate of change in the x direction. If we're moving only in the x direction, we're thinking of y as a constant. So we're just going to differentiate as if y is a constant. We're just going to treat y like it's a number. So let's just do that. What's the derivative of a constant?
0.
Yeah, so the partial of this with respect to x is 0. The partial of this with respect to x is just like the derivative, so it's going to be 12x to the 5th. And what would be the partial of this with respect to x?
2y.
So y is constant. So if that said 10x, the derivative with respect to x would be 10. So it's everything but the x. The 2y is acting like a coefficient. So that's it. F sub y, we're going to get 8y to the 7th. And then how about the partial of 2x to the 6th with respect to y? 0. And then plus 2x. And now you can keep on trucking with these partial derivatives, just like derivatives. We could take f sub x and then partial it with respect to x. This would be the second order partial. And you know what the second derivative measures. The second derivative is measuring concavity. Same thing. Second order partials are going to be giving you a clue as the concavity of the surface. So that's going to be 60x to the 4th. You could also take f sub x and partial it with respect to y. You would get 2. There's f sub x, and if you partial that with respect to y, you would get 2. So let's try that with f sub y. F sub y, partial of that with respect to y is going to be 56y to the 6th. And what about f sub yx?
2.
2. This is not a coincidence. So f sub xy is going to equal f sub yx.
So why are they notated like that? Like just f sub x. It feels like it would make more sense for it to be like f prime sub x or something like that.
Yeah, I think they're just looking for the simplest notation possible. So they're saying we want to find a derivative with respect to x. you know, putting the prime up there, you could imagine them doing the x up there just because that's where we put the prime. We put an x instead of a prime. Yeah, I don't know why that notation won out, but
So
that's,
in physics, I got used to doing like the delta f over delta x. Would you be opposed to us doing that
Nope.
on our test and all that?
no, you can do that. It's totally fine.
Yeah, so f of xy is equal to fyx. Is that like a rule for partial derivatives?
Yes. Yeah. Second order partials will always be equal. There's a condition on it that we'll analyze later, but 99% of the time that's true. Yeah, it's very rare that that won't be true. For that not to be true, there's got to be some weird piecewise defined surface type thing going on.
Will we ever need to know triples?
Triple,
Excel.
oh, XXX or XYY. There's a couple of examples where they'll ask you to do it just out of curiosity. But
Acceleration.
yeah, we're not going to do it though. Well, it's the partial of, if we start with f as being position, f sub x is going to be velocity, f sub xx is going to be acceleration, f sub xyy or xyx or whatever is going to be jerk.
And then snap.
Snap, snap,
Crackle.
pop. All right, so let's try this one. How about g sub x and g sub y?
Wait,
What's that?
you're doing G sub y instead of G sub z?
Oh, why would they put a z in there for? Oh gosh.
Make sure you're paying attention.
Yeah, make sure you're paying attention. All right, you guys try g sub x and g sub z. Can you dig it?
I cannot.
You gave up quickly.
You can do it. I pay.
You didn't give me a shovel, first of all, so.
You don't need a shovel for this one. Just a pencil. Let's see here, with respect to x.
It's not gonna look at mine. I don't think that's, I know that's partly right.
Good, good. Yeah, yeah, that's right. Yeah, with respect to z is a little easier than with respect to x.
I think those are two.
You should be dealing with quotient, product rule.
Yeah, okay, so the two.
Product rule,
X.
first one. Product. You have two functions of
So the
x.
derivative of x would be 1.
Two
So
functions
you're
of x means product rule.
Oh, is it product or?
Oh, you did print that.
Yeah.
Did you see the one? Did you hold that up?
The one he has?
Yeah.
Yeah, I found one of the papers for this one.
Oh,
I tried
1
to
over
make
the inside, right?
the layers.
Yeah, but then you have to take the, you have to multiply.
Like, I
the
printed this
inside
as
tight enough to-
by 2x.
Yeah, so this is a 40 by 40.
Uh-huh.
And then I figured out the
Let's say it's
length
2x.
here.
Yep.
And then I pretty much made that here.
Exactly that way.
And then I took off like 2 millimeters just so it kind of like clamped together. But it didn't. So it's probably just. But yeah, if I'm
How long
gonna
did it
say
take to
it's
print out?
This took an hour.
Took 1 hour to print?
Yeah, that's
And
nice.
is it solid?
Yeah, it's completely solid.
And then this took how long to print?
That took about an hour as well.
Oh, that's pretty. It's really cool. It's amazing. It's amazing. That's what we're taking to outer space, right? 3D printer.
I think it's first derivative, second.
Okay, so first
3D modeling.
Yeah.
derivative of second or partial of second, however you want to say it. So that's first partial second. Partial of a log is 1 over the inside times the partial of the inside, plus second times partial first.
And then you can
So we
factor
get-
out x on the first term.
So yeah, this will be a 2x squared then up there. We know you meant. So 2x squared, and then partial with respect to z, the x is just constant, so that's just going to come along for the ride. So when we partial this with respect to z, we get 1 over the inside times the partial of the inside with respect to z. So we're going to get 2xz. You get it? Any mystery on any of the letters here? Are we good? All right. How about this one? Quotient rule?
Why do they have to do those letters?
I know, U and V. Switch with X and Y if you want. So H sub U. All right, so we have a lot going on. So we have the outer function, which if you want, it's probably helpful to write it as a 1/2, just so you can see clearly where the base is and what the exponent is. So we're going to do 1/2 the base raised to the power less 1. And now we have to take the derivative of the base, which is a quotient. So the derivative of the base is going to be low partial high with respect to u minus high partial low with respect to u over low squared. There we go. There it is. Okay, so then in the numerator, is there any cancellation up there? It looks like uv is going to cancel. We're going to have minus uv here, but we're going to have a plus uv there. So that will go away. So we're going to end up with, well, let's see, 1/2. I'm going to just flip this over so that we can have a positive 1/2. And then over here, we're going to have a minus v squared divided by u minus v squared. And there's not a lot left here. We can combine the u minus v's, and that's about it. All right, so this will end up being, oh, I guess we can cancel a v too. Well, yeah, there's still a little bit of work to do. Let's see if we can do it without making any mistakes. So u minus v in the numerator to the 1/2 power, in the denominator to the 2 power, so that gives us a u minus v to the 3/2 in the denominator. We have a v squared in the numerator and a v to the 1/2 in the denominator. So that's going to be a v to the 3/2 in the numerator. And then we also have this u to the 1/2 in the denominator. So that I'm going to squeeze in right there, u to the 1/2. 2 u to the 1/2. So I think we got it all taken care of.
Why did that go in the denominator?
Why did this u go in the denominator? Right here we have a square root of u and a square root of v.
Oh, so you just
Why
to
did I
get
flip
the
these?
negative.
I flipped those to get rid of the negative. Flip those to get rid of the negative. And then in the denominator we have a square root of u and a square root of v, so the square root of v can merge into the numerator and change that. The square root of u has to stay in the denominator. The square root of u minus v can merge into the denominator and change that. Yeah.
How did you get a negative v squared?
A negative v squared, because right here we have u times v minus u times v, so that cancels, but then we have minus v times v. This v here distributes to both of those.
Oh, okay.
So that's v times u, which cancels there, but it's also v times v.
Okay, that makes
V times v, v squared. All right, so that is h sub u, and h sub v is similar. H sub v is similar.
It looks nasty.
Yeah, nasty. Nasty. Any other questions on how we got anything in there?
HV is similar.
Got it? You sure? Yes. Such a convincing yes. All right. You sure? You can ask a question.
Nope.
Okay, so here's the mixed partial thing. So we're going to see that f sub xy and f sub yx are always going to be equal. And the only condition is that the partials exist and are continuous on the domain. So as long as those mixed partials are continuous, they're always going to be equal to each other. To get a situation where they're not equal, you literally have to build a crazy discontinuous function. It's not easy to do. So for us, I don't know that we'll ever see an example where they're not equal. So let's just demonstrate this. F sub x, what's that going to be here? Partial of that with respect to x.
So that means y is a constant.
Mhm. E to the y. So it's e to the y times x. So it's a linear function of x, where the coefficient is e to the y. And the derivative of a linear function is the coefficient. The coefficient here is e to the y. Hmm? So what would f sub xx be?
0.
Yep, 0. What would f sub xy be?
Y to the y.
E to the y. So let's go with f sub y. F sub y is going to be x e to the y. Good. Does everybody follow that? X is constant if we're partialing with respect to y. So x comes along for the ride because it's a constant. The partial of e to the y with respect to e to the y is itself times the partial of the exponent, but that's just 1, so we get that. And then how about f sub yy?
X e to the y.
X e to the y. And then how about f sub yx? E to the y. Mhm. So that'll always be the case. So in Calc 1, you guys learned how to, what was it called? Classify critical points. You figured out maxes, you figured out mins, and you had a first derivative test, you also had a second derivative test. Same idea here. We're going to have a surface that's undulating, and we're going to want to find the high points, we're going to want to find the low points. And so we're going to create something called the second partials test. And we'll be using these partial derivatives here, these second order partials, to create a test. If we imagine our surface, for there to be a max or a min, there's going to have to be a horizontal tangent plane that's kind of analogous to a tangent line. If we had just a curve, we had a horizontal tangent line. Now we're going to think about a tangent plane. And then we're going to have this second order partials test that's going to figure out if you have a max, a min, or neither. Saddle point. Okay, how about this one? F sub x. So we treat the base as xy, so it's 1/2 times the base, subtract 1 from the exponent. And then what's the partial of the base with respect to x? That's y. So if we wanted to rewrite this just to clean it up a little, we would have 2 divided by, we would have y divided by 2 times the square root of xy. Now let's skip f sub xx here. Let's just do what they asked us to do. Let's go straight to fxy. F sub xy. So f sub xy, we might, let's simplify this a little more. Let's go a little more. There's one more simplification step that's going to help here. That simplification step is going to be to merge the y's. Let's do it like that. And now we can find f sub xy more easily. Let's avoid quotient rule whenever possible. So we have that. So we're going to partial that with respect to y. The denominator is just constant with respect to y, so that just comes along for the ride. It's going to stay there. So we really are just dealing with the numerator, half y to the minus 1/2. So we're going to get 1/2 y to the minus 1/2. So 1/2 y is going to make that a 4. So the negative 1/2 puts it down in the denominator, so we get this. Any concerns? right, let's take a look at f sub y. It's going to be identical, right? It's going to be, because the inside has got so much symmetry to it, f sub y is going to end up being this, which you can convince yourself of. And then if we did f sub yx, we do f sub yx, we're going to go through what we just did. If we partial this with respect to x, we're going to get 1/2, so that makes it a 4. X to the minus 1/2, that's going to push the square root into the denominator. And then, of course, those two are equal. So mixed partials will always be equal. Oh! Let's take a break. Let's take a break before we look at that nasty thing. Yeah. You need to have a formal definition of what it means to be differentiable. And that formal definition has to fit with our intuition for what it means. In Calc 1, we know that we're trying to figure out something that's going to tell us whether a curve is smooth or not, whether it's got no corners or cusps. We want to figure out a definition for differentiability that is going to figure out if there is a unique tangent line at a given point. And that limit of a difference quotient is what works. You form the secant line, you let the secant line rotate into the tangent position, and if that limit exists, then there's a tangent line and you say it's differentiable. And like I said earlier, you guys used that for about a week, and then you learned the power rule, and you're like, whoa, why do we have to use the definition ever again? And you don't. Here, the definition we will never use, look at that thing. So the definition to be differentiable for a surface is a lot more complex because the idea is similar. If we have some sort of surface and we want to determine if it's differentiable at a point, the idea is that we are trying to find a tangent plane. We want to know, is there a tangent plane? Yeah, that's not a good tangent plane. Bad tangent plane. We want to know whether there's a unique tangent plane. Yeah, I don't know if we can find it. So if we're at a particular point, we're trying to figure out if there's a tangent plane that's unique at a given point. And so the idea is that we'll take kind of like a secant plane and we're kind of rotating it to see if we can get to a unique tangent plane position. And this is what it takes. You've got to find your partial derivatives, but then there's these extra two constants, these extra two epsilons that are literally close to impossible to ever find. And so you've got to use this definition, you have to be so clever, and it takes way too much brain power for anyone to ever use.
Pretty much one of those questions would take up an entire test period.
Yeah, it would take an entire sheet of paper to prove that a surface is differentiable by that. So what we need is a better technique. We need to be strategic. And the idea is simple. We know how to figure out the partial derivatives. So if we have a surface, we can imagine it being differentiable. Differentiable intuitively means that it's smooth. You should be able to slap a tangent plane on there that would be the best linear approximation to that surface. And the idea is going to be simple. The idea is going to be, well, if you imagine your point of tangency, so we've got our surface, you imagine your point of tangency, and then you imagine all the curves that go through that point of tangency. If every one of those has a tangent line, the collection of all tangent lines are going to form the tangent plane. So if we look back at that picture that we had on the board earlier, where we've got our surface, and they had one curve, through that surface. So if that's our point of tangency right there, if you imagine all possible traces coming through your surface through that point, all possible curves through that point, and you just collect all the tangent lines, that collection of all tangent lines will be the tangent plane. So the idea is going to be more simple than this. We're going to say, if all directional derivatives exist and are the... Oh, welcome back.
Hi. We had the printer.
So if it is differentiable in all directions, all directional derivatives exist, then it's going to be differentiable. You know, so intuitively, we have to have this unique tangent plane, and then we're going to find a better way to figure it out. So we'll do it. We won't use that. That's just theoretical. So let's talk about the conditions for differentiability first, because there is your instinct. In Calc 1, if you can take the derivative, it's differentiable. Right? If you're given a function and you can take the derivative and you get a function, it's differentiable. Right? And the only place where it's not differentiable is if you have division by 0 or the square root of a negative. Like, it's so easy. If you're given some function, y equals x cubed, if you can take the derivative, oh, it's differentiable. Right? That's it. If you get a derivative, it's differentiable, as long as you don't have division by 0 or square rooting of a negative. But now let's check out this weird example. We had this up here before when we were talking about limits. Let's talk about this same example with respect to partial derivatives at the origin. So again, we have the xy plane, and the function value is going to be 0 unless you're on an axis. If you're on an axis, your function value is 1. So you've got this floating cross up here. What is f sub x at the origin? So what is the rate at which the x values are changing as you move towards the origin? Or excuse me, what is the rate at which the function values are changing as you move towards the origin along the x-axis? 0. Right? You're on the surface, you're going in the direction of the x-axis, you're coming in along one of these floating lines here. The y values, the z values are all 1. So the rate of change is 0. The z values are repeatedly 1, 1, 1, 1, 1, 1, 1, 1 as you're coming towards the origin. So that tells you that f sub x, as you approach the origin along the x-axis, the z values aren't changing. They're all 1. So that direction, 0. What about if you approach the origin along the y-axis? Yeah, still 0. Okay. So now, there's a part of us that wants to say, oh, if both partials exist and are equal, it's got to be differentiable. But would you ever want that to be a differentiable surface?
No.
No, it's got a big tear in it, right? It's discontinuous. We already found that the limit doesn't exist at the origin. We definitely don't want our definition of differentiability to include something like that, which means it's not enough for the partial derivatives to exist. Just because the partial derivatives exist, that's not enough to then say, oh, it's differentiable at that point. Because we don't want our definition to include weird surfaces that have parts of them torn out. Okay. Okay, so it's not enough. And here is the theorem that we are going to use. So oh no, not that theorem. So what's going to happen is that in order for a surface to be differentiable, the partial derivatives need to exist and they need to be continuous. Okay? So you may just naively look at this and say, oh, that's a continuous function. But remember, we talked about continuity last time. There's 2 things that have to happen for a function to be continuous. For a function to be continuous, remember, we have to have the limit of the function as we're going to our point in question. So xy going to x naught, y naught. So we have to have the limit. It has to be equal to the value of the function at that point. So the limit and the value have to be the same. So we found the value of f sub x at both these places, but didn't we already figure out last time that the limit of the function doesn't exist? Right? The limit's not going to exist as we go to the origin. So if the limit of the function doesn't exist, the function can't be continuous. If the function is not continuous, it can't be differentiable. For a function to be differentiable, it at least has to be continuous. And so if it's not continuous, it's not differentiable.
Although, yeah, where does the partial derivative play in this test here?
So these partial derivatives aren't continuous because the idea of continuity with the idea of continuity here is you're coming in towards the origin, the partial derivative there is 1, but when you get really close to the origin, if you're dealing with a continuous function, if this was a continuous function, you should be able to turn and just move a little bit to the side and have close to the same function value. And we don't have that here. If you just move a little bit off this x-axis, if you turn a little bit there, this function is no longer defined. You're going to have an f sub x that does not exist. So these things exist, but they're not continuous. The simplest way to look at it is if your surface is discontinuous at a point, then, or let me say that again, if the limit does not exist at a point, it cannot be continuous at that point, and if it's not continuous, it's not differentiable. That's the sequencing. For it to be differentiable, it has to be continuous. So for this surface to be differentiable, it has to be continuous at that point, but it's not continuous there, so it's not differentiable.
So pretty much the partial derivative is pretty much useless for determining if it's continuous or not?
If you have a discontinuous surface, if you have a piecewise defined surface, then it's more complicated. If we have a regular surface that's defined, that's not piecewise defined, then we just look at the partial derivatives and we can tell if they're continuous or not. But when you have a piecewise defined function, then it's a little stranger.
Okay.
But these partial derivatives are not continuous on that surface right there. Those partial derivatives are not continuous. But the thing in your mind should be, if it's differentiable, it's continuous. Which means, so the most important thing right now, if it's differentiable, that means there's a unique tangent line, and the image in your mind, you've got your curve, you're imagining you're rotating your secant line. So you've got the secant line, and you start rotating it, okay? And then if it rotates into the tangent position, if that all works, that's the limit of the difference quotient, then it's differentiable. And obviously, the function, if it's differentiable, it's got to be continuous because you're rotating in both directions, you know, sort of rotating into the tangent position. So if you can rotate into the tangent position, there's no way there can be a break on the surface. So if it's differentiable, it has to be continuous. And logically, what this means, the most important conclusion here, is that not continuous means not differentiable. So if it's, so that's called the contrapositive. So if A implies B, then not B implies not A. So in logic class, they'll call that the contrapositive. So if you have A implies B, you can just as equally say then not B implies not A. So not continuous, no way it's differentiable. So our surface up here, it's definitely not continuous, so it's definitely not differentiable. Okay, so let's do a few problems. This one is just a simple partial derivative problem with more than one variable. So find the first partial of the following function, so q sub x. I don't know why they put some of these where the powers on all the variables are the same. Sort of. You feel like you might be, let's change it. Let's make it tangent of xy squared z cubed.
But why?
So that we don't,
That's not redundant.
what's that?
Isn't it like redundant if you have to just?
Yeah, but if they all have the same power, you might be making a mistake and not realizing you're making a mistake because you can't really distinguish the difference between the partials. Okay, so derivative of tangent is secant squared of the same inside times the partial of the inside with respect to x. And what's the partial of the inside with respect to x?
Y squared z cubed.
Y squared z cubed. And then q sub y. First part's going to be the same. First part is the outer function. So the derivative of the outer function is secant squared, so it's secant squared of the same inside. And then how about the partial of the inside with respect to y? There it is, 2xyz cubed. 2xyz cubed. And how about qz? Same for the outside. And then derivative of the inside, or the partial with respect to z?
3xy squared z cubed.
Yep, 3xy squared z squared.
Oh, z squared.
Is that what you said?
I said cubed.
Cubed squared.
Yeah, I forgot to.
Subtract 1.
Yeah.
Subtract 1. Any questions on any of those partials? So, doesn't matter how many letters there are. Just do what we normally would do. All right, let's do a hard one. All right, so here's a piecewise defined function. So first, let's decide if it's continuous at the origin. So this piecewise defined function, the value of this piecewise defined function is 0 at the origin. So now we need to know, is the limit of the function also 0? For it to be continuous at the origin, the limit and the value have to be the same. So let's take the limit of this function as we go to the origin. So the limit of 2xy squared over x squared plus y to the 4th as we go to the origin. I can get right in there very easily. Okay. So if this limit is going to exist, we might need a whole new page to write this. So we obviously, if we plug in the origin, we get an indeterminate form. We get 0 over 0. So we have to go back to thinking about limits and the two-path thing. If this limit is going to perhaps not exist, we could find two paths that have different limiting values. So let's just check. Let's do a couple of paths just to see if we suspect whether it's continuous or not, or whether the limit, whether the limit exists or not.
But could we use polar?
We could definitely use polar. That would be a way. Will definitely work. Polar is definitely going to work. But we're going to first try it this along paths here. So let's. Well, I guess it's not an example. It's just a continuation of that function. So somebody tell me what that function was. It was
2xy squared divided by x squared plus y to the 4th.
I'm sorry, say that once more.
2xy squared divided by x squared plus y to the 4th.
Okay, so there's the function when we're not at the origin.
Square.
So is that right?
Yes.
Okay, so let's investigate this limit. So let's first check along, let's just check along y equals x. So let's go along y equals x. So if we're going to go along y equals x, we're going to get the limit. We're going to plug in a y for all the x's, or vice versa, whatever floats your boat. And then we end up with y squared plus y to the 4th divided by, or not divided by, but as y goes to 0. And what happens here? Does that give us anything?
Nope.
Or we also get indeterminate form?
So we get indeterminate form, so we're down to one variable though, so we can
Use L'Hopital's?
L'Hopital's rule. So we can just start L'Hopital-ing this thing down, and what are we going to end up with?
Definitely 0.
right? Everyone agree 0?
Mm-hmm.
Do you agree? So another way to think about this is that the dominant term in the denominator, well, it doesn't really matter when we're going to 0 so much. But if you start differentiating, this derivative is going to go away quickest. This one is going to go away next and become 0 when this is just a y with a constant in front of it. And we're going to get 4y cubed and then 12y squared and then 24 to the y. So this will end up being 0. We do that. Or what about if we came along an axis? Let's come along an axis. That might even be another way to think about it. So let's come along, say y equals 0. So if we come along y equals 0, we're going to end up with the limit. If we plug in y equals 0, we're going to have this, which is also 0. So there certainly seems to be a lot of paths where the limit is 0. If we came along x equals 0, bless you. Along x equals 0, don't we also get limit? So if x is 0, we get a 0 over y to the 4th. So that limit is 0. All right, so we have all these limits where we're getting 0. Now let's try this path. All right, I'm going to try this path. So let's go along x equals y squared. All right, so first off, when I look at this, you might say that, why would you even think to do this? So I'm going to put in a y squared just because the denominator will combine pretty easily then. So along x equals y squared, we're going to get the limit of 2y to the 4th over y to the 4th. Did I do that right?
Oh,
So
2
y
to the 4th.
Yeah.
On the bottom, right?
On the bottom?
Because you should get y to the 4th plus 1
Yes,
to the
2y to the 4th. Thank you. So we get 2y to the 4th there. Everyone agree with that? So y squared there. So we get y to the 4th plus y to the 4th is 2y to the 4th. Y squared times y squared is y to the 4th. So what is this limit? 1. So along that, we see that, oh, okay, we have a different limiting value, so therefore the limit does not exist because we have 2 different values along 2 different paths. So our conclusion is that the limit does not exist. So therefore, limit does not exist.
Therefore, it is not continuous. Therefore, it is not differentiable.
That's true, yes. So, right here, is it continuous? No, because the limit does not exist.
For the first limit that we computed, wouldn't you already get a limit that doesn't exist?
Right here?
Yeah, because you end up with, after you go through and take it down to 1y, you should end up with a y on the bottom and a constant on the top. So then you'd have a non-existent.
But you end up with a 0 on the top. Right, because you get y, you differentiate y cubed once and you get 3y squared, then you get 6y to the 1, and then you get 6, and then you get 0.
Okay, but wouldn't you?
Oh, are you saying that there's still a constant before you? Let's,
Well, I mean-
let's check, let's just do it. You might be right, I didn't work it all the way out. I just picked this for the heck of it. So let's check. So if we do L'Hopital's rule once, we get 6y squared over 2y plus 4y cubed. All right, that's indeterminate. So then we do limit of 12y divided by 2 plus 12y squared.
Okay, cool.
Now here, we can plug in the 0 and we get 0 over 2. So we do get 0. Not for the same reason I was actually thinking, though. So we do get 0, but yeah.
How would we recognize to keep testing if we've already gotten 3 limits and it?
On a test, I will tell you, show that this limit does not exist. Yeah, I won't make you guess whether it exists or not. I'll tell you that, because that's just too crazy to try to figure out sometimes. Okay, so continuous at 0? 0 at the origin? No. If it's not continuous, it's not differentiable. So not continuous means not differentiable. If possible, evaluate f sub x and f sub y at the origin. So let's look at this thing right here. What is f sub x at the origin? What is f sub y at the origin? So if we look here, as long as we're not at the origin, we're up here. So if we're on the x-axis, the y values are 0. So on the x-axis, this turns into 0 over x squared. 0 divided by x squared is 0. So that's 0. F sub y. So if we look at this, the function values on the y-axis, we're plugging in x equals 0 on the y-axis, so we get 0 over y to the 4th. So again, 0. So here we have both partial derivatives being 0, but we have that the function is not continuous and not differentiable, even though these partials exist and are 0. So determine whether f sub x and f sub y are continuous at the origin. So can these be continuous at the origin if it's not differentiable? No. They cannot be continuous, because if these were continuous at the origin, then it would be differentiable, because that's the definition or the theorem that we are going to use to confirm differentiability, that the partials exist and are continuous. So if the function is not differentiable, there's no way the partials are continuous. So no. And all right, so down here, what did I do down here? Oh, I found f sub x and f sub y. Okay, let's talk about this. So we used a theorem to sort of conclude that no. Let's come down here and try to do it more algebraically. So that we used the theorem because it's not differentiable. There's no way those are continuous, because if they were continuous, it would be differentiable. So let's look at these. All right. So we said that f sub x and f sub y, we said that the value of those is 0 at the origin. Or we said that let me restate that. So f sub x and f sub y are 0 at the origin. To figure out if they're continuous or not, those functions should give us 0 no matter what path we come in to get to the origin. So f sub x and f sub y, we're coming into the origin along the x-axis and the y-axis. So let's analyze these two things coming along another path. Let's analyze coming along this path, x equals 2y squared. So if you want to, you can check your partial derivative skill set, taking the derivative of this with respect to x and y. I just did it there so we can analyze without going through the rigmarole of finding those partials. So let's plug in. Let's see. So along x equals 2y squared. So let's plug that in. So we're going to have 2y squared, y to the 4th. Now let's replace that. We're going to get 4y to the 4 divided by 4y to the 4 plus y to the 4 all squared. And let's simplify that. So it's going to be minus 3y to the 4th multiplied by 2y squared. So minus 6y to the 6 divided by 5 squared is 25, y to the 8th. So that equals minus 6 over 25y squared. Okay, so what happens then when we are when we're coming into the origin there? So if we come in along this path, what happens there? Does the limit of this exist? So this is a DNE. As we're coming into the origin here, y is going to 0, so that's blowing up, so that does not exist. So this function here, if we are coming in along this path, we get a limit that does not exist. So that means that that's not a continuous function because the limit does not exist. And the same is going to be true here. If we come in along this path, we're going to get a limit that does not exist at the origin.
Is that always true? You get does not exist for one.
Not necessarily.
Okay.
You could, if you have it does not exist for one, then you know it does not exist overall. But you could have, you know, we've seen some limits will exist and some won't. Depends on the path. So that just shows us algebraically what we concluded theoretically above, that this function is not a continuous function because along this path it has a different limiting value. So when we went along the x-axis, one thing, but along this path, different.
No, I'm saying for fx and fy.
Right, yeah, so it's possible that this does exist along that same
Okay,
path.
it
It's
does.
possible.
It's
It's
possible.
possible. In this case, it won't, though. We'll have the same thing. Yeah. Okay, so the two partials are not continuous, so therefore the function is not differentiable. Let's go to, oh, we're ready for the next section.
Would you be okay with us just using the theorem? And
Yeah.
not having to go through
Yes,
this stuff?
yeah, the theorem is totally fine. That's what we're going to use 90% of the time. Yeah, using the theorem is enough. If it's not continuous, it's not differentiable. Totally fine.
How many trees are we expected to really go for to determine differentiability? Like this along the y, along the x, along x, y?
Yeah, those are the paths that we usually test. And if something, if the question says show that it's not differentiable, or show that the limit does not exist, and you've tried x equals 0, y equals 0, and y equals x, then you might have to look at it and try x equals y squared or y equals x squared. It should be, but you're looking for a path. If it says show that it does not exist, it's got to be a path. It can't be too complicated. Maybe x squared, maybe y squared, maybe square root of x, maybe square root of y. It's not going to be too complicated.
This is what I remember. This is my old friend.
The chain rule?
Yeah.
Yeah, chain rule is your buddy. Okay, so that's the chain rule you all know and love. Right? So we have one independent variable. So we're imagining that z is a function of x and y, and we're imagining that x is a function of t, and we're imagining that y is a function of t. So that's how we kind of write it mathematically. This says z is a function of x and y. This says x is a function of t, and that thing says y is a function of t. So x and y are both functions of t. Now, this means that z is a function of just one variable, t, through the x and through the y. So as t changes, y changes. As t changes, x changes. And as x and y change, z changes. But it's legitimate to ask, what is the derivative, not partial derivative, what is the derivative of z with respect to t? You can only do a regular derivative when there's only one independent variable, f prime of x. And so here, because z changes with respect to one variable, we can talk about the derivative. We don't have to talk about partial derivatives. And so then here's our chain rule. So we're going to get the change of z with respect to x. Now that has to be a partial because z depends on both x and y. So we take the partial of z with respect to x, but then the derivative of x with respect to t because x is a function of only one variable. So if you wanted to, you could write this as z sub x, x prime, plus z sub y times y prime. You could write it that way. So x and y, regular derivative because they're functions of one variable, but derivatives of z have to be partial derivatives because z is a function of two variables. So let's try our chain rule. Okay, so we have z equals xy squared. So if we want to find the derivative with respect to t, first let's do it the kind of more intuitive way where we say, hey, well, if it's a function of t, let's just turn everything into t's. This way is very simple. We did not use the chain rule here. Here we use substitution. We said, let's convert x to t squared, let's convert y to t, let's combine those so that we've written z as a function of t, and then do the regular derivative. We get that. Now let's try it using the chain rule. We should get the exact same thing. So dz dt will be the change in z with respect to x times the change in x with respect to t plus the change in z with respect to y times the change in y with respect to t. So let's see if we get the same thing. So z sub x is y squared times x prime is 2t plus z sub y is going to be 2xy times y prime, which is just 1. So we're almost there.
And then you do your substitution.
And then we do our substitution. So at the top one, we subbed and then differentiated. Here we differentiate, and then we're going to sub. So y squared, that's a t squared. So we end up with 2t cubed plus 2xy, that's 2t cubed also. So we end up with 4 times t cubed. So it's not going to matter which way you go. So the chain rule, many people like to go, the substitution and then derivative method. It's totally fine. But if it asks you to do the chain rule, you want to be able to do it that way. Not bad. Not too bad. Okay, so here, Q is a multivariable function. Each of its variables is a single variable function. So we have 2 choices. Let's do it the substitute and then derivative method first. So if we want to substitute first, we're going to end up with sine squared plus cosine squared plus cosine squared?
Cosine squared?
Yeah, so we're going to end up with sine squared t plus cosine squared t plus cosine squared of t, which will, of course, simplify into 1 plus cosine squared of t. So we get that. So then the derivative, we'll use the chain rule. So q prime of t, or dq dt, dq dt. We're going to have half the base. You know what we're going to do. So we're going to get that in the denominator. And in the numerator, we get the derivative of the inside, which is minus 2 cosine t sine t. So I end up with that. So that's substitution followed by regular derivative. Now let's try the hard way, the chain rule way. So dq dt. So now we have 3 independent variables here. Q depends on x, y, and z. So we're going to have 3 terms here. So we're going to have q sub x times x prime plus q sub y times y prime plus q sub z times z prime. So we have to have a term for each independent variable. Okay, so what is q sub x? Q sub x, that's the partial with respect to x, so we're going to get 1/2 times the base raised to the minus 1/2 times the partial of the inside. So we're going to get partial of the inside. We're going to get 2 times the square root of x squared plus y squared plus z squared. Multiplied by x prime, and x was equal to sine of t, so the derivative of that is cosine t, plus q sub y, same exact as q sub x, except that we have a 2y in the numerator. And we'll cancel those 2's in the next step. And that one was cosine, so the derivative will be minus sine. And isn't the last one identical?
Yep.
So we're gonna have 2z, and that one is gonna be a minus sine of t also, and then the same denominator. Whew.
Why would you ever do it this way?
I know, this way's always longer. It's always longer. All right, now let's go back up and convert. So x, y, and z, convert them to the trig functions. And we know that q is going to be, or whenever we see a square root of these squares, we can write it as square root of 1 plus cosine squared. So this is going to be equal to, x is sine, so we have sine t, cosine t. The denominator is square root of 1 plus cosine squared. So that's that one. Minus 2 times y, which was, y was cosine of t, right? So we're minus 2 sine t cosine.
Cancels out.
Oh yeah, thank you. Yeah, the 2 can just vanish. Let's get rid of it. That. So these guys just cancel, don't they? That. Just want to let me think. What's our target? Our target. Oh yeah, good. It is. Oh, we just didn't cancel the 2's up there. So this is just use.
Thank you.
And then minus, and then we have what we're looking for. Sine t cosine t over the square root 1 plus cosine squared of t. And these two just cancel. So that is our final answer right there. And that, of course, matches what we had up here. And yeah, Terrence's point. Can we substitute before we take the derivative? The answer is yes. The chain rule is more of a theoretical thing. There's going to be times where they try to walk you through the chain rule, though. Oh yeah. But it's more theoretical.
Oh, they do.
Oh, they do. All right. Any question on any of those little pieces in there? The z primes, the y primes, x primes. Do you get when you can use a prime and when you can't? So you can use a prime for a one variable function, but you have to use a subscript for a multivariable function. When you're doing a partial, you have a subscript. When you're doing a derivative, you have a prime. So a derivative is for one variable, partial is for multi. Now, now let's assume that z is a function of x and y, like we just did. So z is a function. You can see it's a function of x. You can see it's a function of y right there. So z is a function of x and y. So z is a function of x and y. But what do we notice about x and y? X and y are now functions of two variables instead of just one. So z is a function of x and y, and then x is a function of s and t, and y is a function of s and t. So now you cannot say z, dz, ds, or dz, dt. You have to do partial z, partial s, or partial z, partial t. Because z is not a function of one variable anymore. It's a function of two through x and y. Like this one here, let's see, was it right there? Right here you have the derivative of z with respect to t, because z is changing with respect to only one letter, t. But now it's changing with respect to two letters. So you can't do dz, ds, doesn't make sense, because it has two independent variables now, s and t. So we have to go, so to get the partial of z with respect to s, we're going to have an x sub s and a y sub s, because x and y both change with s. So let's try it. Should we do the substitution method?
Yes, please.
Okay, let's do the substitution method. So here is our function, z equals sine of 2x plus y. So x and y are going to get plugged in here so that we have s's and t's instead of x's and y's. So 2x. So 2x plus y, so we're going to have 2s squared plus 1s squared, that's 3s squared. And then minus 2t squared plus t squared is minus t squared. So there it is substituted first. And that makes sense to then ask what is z sub s, which you could write as the partial of z with respect to s. It also makes sense to ask about z sub t, which you could write as the partial of z with respect to t. Okay, so cosine of the same inside, the same angle, multiplied by the partial of the inside with respect to s. 6s. So that is partial of z with respect to s.
Success.
Well, I thought you said the word success.
I did too.
Like
Success.
Like
What?
that's
Success.
laboratory stuff.
We did it! Success! Success. Success.
English is fun.
It's going to be like that, what's that YouTube thing? Right, those words that people were saying and everyone was hearing something different?
Oh, I can't remember.
I don't even remember what
Yeah.
the
Yanny or whatever.
What was it?
Hold on.
Yeah,
Laurel and
Zanny?
Yanny.
Yanny.
Yanny and Laurel? That was so weird.
It's Laurel,
Once
by
you
the
hear
way.
it one way, it's really hard to hear.
Yeah. I can't remember which one I heard now. I heard one and my wife heard the other.
It's really
She
funny.
was getting mad. She's like, you can't hear it! It's like, no, you don't hear that.
The thing is it's low sound wave, so
Mhm.
it's actually saying Laurel, but because it's so low, it can be interpreted twice in your brain.
So the actual word is Laurel?
Saying
The
Laurel.
actual thing that it's saying is Laurel.
Well, maybe
People
it's
are
saying
hearing
Yanny,
Yanny
but it's
because
just
of
being
the
said so
frequency?
high
Yes.
that it sounds like Laurel.
Wow, that is so, because those words don't even seem anything alike.
Mm-hmm. It's so weird.
That's the weirdest thing. I could
Anyway, science.
Yeah, that is crazy.
Science.
In the name of science. Okay, so dz, or partial z, so this we call partial z partial t as opposed to dz dt. This script symbol d we usually just call partial z partial t. So partial z partial t, we're going to get cosine of the inside multiplied by negative 2t.
I spent so much time doing this the long way.
Yeah, doing it the long way is painful.
Do they make you do it the long way?
They try to inch you through it one step at a time.
They tried to.
Yeah. So in a,
That sucks.
And then you like accidentally do 2 steps in one, and then you have to start the whole problem
Yeah,
over again.
They're all like my
Oh, that's the worst.
Okay, so why don't you guys try this one? Find z sub s, z sub t. And I don't care if you feel like you'd rather substitute and then differentiate with partial derivatives. It's totally fine. Doesn't matter. The chain rule piece of it is more of a conceptual, more of a theoretical thing than anything in practice when you're doing this type of chain rule.
Can you go up just a little bit?
Oh, I'm sorry. That far? Is that far enough?
Yep.
All right, so find z sub s and z sub t. Z sub s and z sub t.
The S's weird me out so bad.
Don't you hate s?
Yeah, it looked like you had 35 up there.
And my
I
T's
know.
look like partial D, like partial derivatives. So it just is getting
Yeah,
lost.
s is the worst. Pick a u and a v. U and v are better than s and t.
I don't know.
That's up for debate.
Yeah, I mean, I guess, but I can make my u's not. My u's don't look like any number.
I'm just
It's
gonna
so hard to
put
make an
together
s not look like a number.
You are.
I'm gonna try.
So that means that means that you just wrote a T again.
Welcome to my brain. I've done this like 6 times in a row.
So S means
Well, that actually spins really well with the rubber band.
okay.
Yeah, so this one will just turn into
Look at that.
minus sine squared.
That's a good idea.
Why?
Because it's cosine of s, so if you take the derivative of cosine of s, it's minus sine. S.
It's hard to tell.
So it would be minus sine of s.
You're gonna pay the price. You're gonna heat a cube.
Oh my gosh.
Is it working?
I'm a little bit confused because the last one we had S and T both X and Y.
Yep.
It seems like these are one variable.
So T is a constant, so you oh, that makes sense. So just
That's a good point
That
though,
makes sense, yeah.
because
So then this is just
they
a
are
constant,
separated,
so
so
this
you
would
might
go-
think you can just do a regular derivative, but you
Yes,
can't,
yeah,
because
yeah,
once you
yeah,
plug
yeah,
them
okay.
in, your
That
Z
makes
is
sense.
gonna have an
So
S
then
and
you have
T.
plus 2
So you
sine
still
of
will
S.
have,
So that would be
but if you were gonna do it the chain rule way, dx, or a partial x with respect to t would be 0.
Okay.
Wait, that's not as
Right,
bad as I
and then the
Okay.
partial of y
So
with
then you
respect
take
to s
and
would be
then
0.
this
Okay.
is-
So you'd have some of it
So
zeroing
negative,
out.
Okay,
minus
cool.
And then when you
sine
look
of
at that,
s. Wait, that would be plus 2 sine of s then,
you
right?
substituted.
Because
Yeah, I did.
Something
derivative
for-
of minus 2 cosine of s would be positive 2 sine of s.
Yeah, it's right, the rubber band,
Oh, Rachel did sine
Yeah,
of
yeah,
S.
you would have one.
Right.
And once you have one,
Yep.
I'll be so nice and three vertices are. Very obvious.
It's gonna be cosine of s.
Yeah, well, I had somebody that brought in a cordless drill with a styrofoam one. Styrofoam piece from Michael's.
Should you be getting a T anywhere in partial derivative
where's
with
my
respect to
S?
s?
Maybe.
Yeah, because I'm getting one
So
sine
you
of t.
substituted.
I don't know, this is
Pretty good to me.
It looks a little. This looks
Find out.
weird.
with the multi, like.
Let's
variable
find out.
Yeah, I know.
That's what's weird.
All right, so when we do our substitution, I think that's
Can we? Yeah.
everyone's preference. So x times y is cosine sine. That's great, cosine of s. Sine of t minus 2 cosine s minus or plus 3 sine of t. Okay, so the function z is now a function of s and t. It's a multivariable function. So that makes sense then to ask for its rate of change with respect to each of those individual variables. So if we do z sub s, that's going to be minus, derivative of cosine is minus sine, so minus sine of s. Sine of t is coming along for the ride because it's constant with respect to s. And now this becomes positive 2 sine of s. And then the partial of sine t with respect to s is 0. So that last part is gone.
Oh.
So that's what we have. Sinus, sine t, sine s, sine t. Oh, that's so weird. S's and T's just don't flow off the tongue as easily. All right, so derivative with respect to t, I should say the partial derivative. So partial derivative with respect to t, we're going to get cosine s cosine t. Does not look like English. Minus, plus.
The parentheses.
There you
cosine
go.
t. Yeah, we might want to put some parentheses in there.
Or like a dot.
It looks like alphabet soup.
Reminds me of implicit differentiation, like it doesn't feel right.
Yeah,
There's too many
yeah.
variables in there.
I don't
All right, well, let's do some implicit differentiation then.
Same.
No.
We ready for implicit
No.
differentiation?
No. I know.
Do I want to remember
Have no
implicit
memory of
differentiation?
that.
All right, well, let's remind you. I think
Oh
that
my
was
gosh,
easy enough.
wait, is
Let's
that
see
the
about
next?
this.
Wow.
Implicit differentiation.
Oh no.
I didn't even mean to say that.
Yeah,
Come on,
right.
Haley.
Right,
You
didn't
jinxed it.
Suckering us.
Wow, that was a great, like, great
Segue?
timing. Yeah.
All right, let me remind you. So remember, so if we have something like x squared plus y squared equals 4, that we know is not a function, but we do know that it's differentiable, that it has a unique tangent line everywhere. So we should be able to come up with a formula that builds the slope of all those tangent lines, except for the vertical ones that give an indefinite, or what's it called? Infinite slope. So you had two ways. You can say, hey, let's assume that y is a function of x, and then let's take the derivative with respect to x of both sides. And of course, the derivative of the right is 0. So this is the implicit differentiation way to do it. So then we take the derivative of that, that's 2x. The derivative of that is 2y times y prime. And so then you end up solving for y prime, and you get that y prime is negative x over y. So with implicit differentiation, you frequently are going to have both of your variables in your expression for the derivative. And that makes perfect sense. Because when you're on a circle, if you're on a relation instead of a function, if somebody says go to x equals 1, well, you could be on the top half of the circle at x equals 1 or the bottom half. So y matters. So y has to be in there. With a function, you take its derivative. It just depends on x, right? X is the only, if you say go to x equals 1, there's only one point on the graph. So with implicit functions, there's multiple points on the graph that can correspond to the same x value. Okay, so that's how you did it with implicit differentiation. Now there is another way, and that is using this notation here. We could say that f of xy is x squared plus y squared. So now my perspective is that I have built a surface with a level curve. This circle of radius 2 centered at the origin is a level curve for surface F. Right? You can think of this as z equals x squared plus y squared. This is a paraboloid, and this is one of the level curves. It's the curve where we set the function value to be 4. All right? And here's our second method. We can find dy dx by looking at minus cap f sub x divided by cap f sub y. So this will give us a shortcut method to avoid implicit differentiation and use partial derivatives instead. So let's see watch how quick this is. So dy dx minus f sub x. That's minus 2x. F sub y is 2y. Cancel out the 2. And we get it instantly.
Oh, nice.
So that's fantastic. And the perspective is different, though. So we're building a surface that has the original curve as a level curve. If we build this surface that has the original curve as a level curve, then this is a shortcut for finding the dy dx, finding the derivative. All right, so that's what we're about to do. So here, this is, instead of using implicit differentiation, I mean, they call this implicit differentiation, but that's not what we're doing there. We're just doing partial derivatives. So we're avoiding the implicit differentiation, which most people like to avoid.
Why are they calling it implicit differentiation if it is explicitly not implicit differentiation?
Because, so the reason they're calling it that is that when you have this situation here, that notation is implying that you have a relation and not a function. And the only way that that relation, so if we're looking at our circle here, the only way that this works is if we assume that there is these are called two implicit functions. So the functions that we're finding the slope of the tangent line for are called implicit functions. This approach is an implicit differentiation approach to find dy dx for two implicit functions. So that's why they use the word implicit, but we're not really using implicit differentiation when we use this technique.
Okay.
So yeah, I don't know why they call it that,
I
actually.
haven't finished law school yet, so I can't
Yeah.
quite grasp it.
Yeah.
So what happens if Fy is 0?
So as long that formula only holds as long as the denominator is not 0. Yeah, good point. So this formula here is only going to work. So if that is 0, then we have probably a vertical tangent, most likely.
Is there like another equation we'd use? Is there another
But-
something else we'd
Well,
look
if
for?
if dy dx is infinite, typically you have a vertical tangent line. So you may have to look more carefully to see if you have a vertical tangent or a cusp. You know, if you had one of those curves that has like an asteroid thing, you know, right there, you're going to get an undefined dy dx, but you don't have a vertical tangent. But right here, you're also going to get an undefined dy dx, but you will have a vertical tangent. So it's going to depend on the shape.
Okay.
So if you do have an f sub y equal to 0, then you have to do more analysis to figure out if there actually is a tangent line. Okay, so let's try to do this using the theorem. So here, I'm building a surface that has the original curve as a level curve. Can I do that?
Yes. You can.
Yep, I can. What would the constant value be in this case? Positive 1. If we plug in a positive 1 for f, we will get this level curve. You could also do this. Would this curve be a level curve for capital F? Sure. What would we plug in for capital F? 0. We can do whatever we want. If we want to put a +1 there, we can put a +1 there. Then what would the f value be to give us this level curve?
2.
Everyone agree? So if we plugged in a 2 here, we subtracted, we get a -1, and we get that same thing equal to 0. Yeah. So the constant does not matter. So if we don't put the constant in, totally fine. If you put it in, totally fine, because it's going to vanish as soon as you take your partial derivatives. So we're going to say that dy dx is going to be minus f sub x over f sub y. So minus f sub x is minus 2x. And then f sub y is minus 4y. So we end up with x divided by 2y. That will be our dy dx. So that's the slope of the tangent line along that curve. Yes. All right, we have one more here. So we're going to
negative x over 2y.
Once again?
Yeah, I got negative x over 2y. I think I did
That
something
doesn't
wrong.
sound right.
You might have something going there.
Let's see. So negative f sub x. So f sub x.
Negative f
Oh,
sub
yep,
x.
that's
I
good.
forgot about that part.
I did the same thing.
There's a couple minuses.
Here we go.
There we go. There we have it. Okay, so we're going to create a surface, and that surface has the original curve as a level curve. Namely, if we plug in f equals 3, we will get that curve. So the level curves for this surface, we plug in different constant values to get those level curves, and it doesn't matter. It doesn't matter whether we include the constant or not. And then we are going to find dy dx minus f sub x divided by f sub y. And so minus f sub x. So partial of this with respect to x. The y is going to come along for the ride. The partial of this is going to be 1 divided by the inside, multiplied by the partial of the inside with respect to x. So it looks like we're going to get 2xy. So the 2x is the partial of the inside, but we still have the y that's lingering in front. And then all of that's divided by f sub y. F sub y, we have to use the chain rule. So it's going to be first times the partial of the second. First partial second. Plus, I guess it's called the product rule. Plus second partial first. So we get all that. And then simplify it. That's terrible. Everyone agree with that product rule piece? First partial second plus. Over for this piece?
No, for the ln in the first part there. Can you use chain rule?
Right down here?
Yeah.
Yes. Which we did, right?
Yeah.
So this first one we're using, it's 1 over the inside multiplied by the partial of the inside. So that's the chain rule part of it. And et cetera. You know how to simplify this. Multiply everything through by x squared plus y squared plus 4. Let's not do it. It's too close to pi o'clock. Pi o'clock. Time for a break. Pi o'clock. Time for a weekend. A long break. Snowboarding can't happen yet. Although my kids had some buddies that did the copper thing this summer.
Oh, really?
They learned to do backflips this summer.
Yeah, the glacier scares me.
Since we just finished 12-3 today, or is that going to be extended?
12-3?
Yes. 12-3
Is it
through Sunday.
Oh yeah. Should we make? Yeah, because I thought we were going to finish 12-3
like Tuesday.
earlier. So 12-3 is set for Sunday night. Yeah, so I'll extend that to Wednesday then, or Tuesday. Yeah. Thank you for pointing that out. I can do it.